The purpose of this project was to create a system similar to human facial recognition that can identify individual ants within the same colony. The first step in this process was to collect labeled data of ants. I created an ant habitat to be ideal for data collection. It consists of a data collection area where ants must walk under a camera and be filmed. There are also multiple gates that allow me to isolate ants in the collection area. All of the ants that have not been filmed live in the main living area, while ants that have been filmed are placed in a separate area to avoid duplicate recordings. To video the ants, I used a FLIR machine vision camera equipped with a macro lens. This overlooked a 3D printed channel that was narrow enough so when the ants passed through, they were forced to walk in the camera's field of view. The camera and 3D printed channel were also enclosed in a light box to ensure consistent lighting. Each video only contained footage of one ant at a time and were named sequentially. Once the videos were obtained, I used a YOLO object detector to detect frames with ants and saved cropped images of them. This resulted in each ant having a dedicated folder full of its own images. Next, I ran a script to create a CSV file with all the corresponding labels and image names. At this point, my dataset was ready to be trained on. To identify the ants, I followed an approach based off the ideas presented in Google's FaceNet. FaceNet uses a neural network to output a feature vector or embedding that represents a face. By comparing the embeddings of two different images, you can begin to predict if faces in the image are the same or different by means of clustering or thresholding. My pipeline was structured using the thresholding approach. Two different images would be put into the same network, known as the Siamese network, and two embeddings would be output. I then obtained the distance between embeddings by calculating the norm of the difference between the pair. If that norm is above a certain threshold, the images represent different ants. If it is below, then the images are showing the same ant. The model itself is a convolutional neural network that outputs a 128-element feature vector. To train the model, I used the loss function known as triplet loss. Training with triplet loss can be understood intuitively by giving the trainer 3 images at each training step, an anchor, a positive, and a negative. The anchor is an image of any ant, while the positive is a different image of the same ant, and the negative is an image of a different ant. During training, the model weights will be updated so that the distance between the anchor and positive embeddings is smaller than the distance between the anchor and negative embeddings. This works mathematically because the distances between the anchor positive pair minus the anchor negative pair must be less than 0 with some margin added on. Because the difference between distances must be negative, the anchor negative distance must be larger than the anchor positive distance. The margin is then used to try and push these distances farther away from each other. After the model is trained, a threshold is selected by looping through the validation set and calculating the average value of the anchor positive distances and the anchor negative distances. I then loop through several threshold values in that range and select the threshold that yields the highest accuracy. Using that threshold, the model was then tested on 2 different datasets, one containing different images but the same ants as the model was trained on, and the second containing completely separate ants. For the dataset on familiar ants, the model achieved a true positive percentage of 95%, a true negative percentage of 99%, and an accuracy of 97%. On the dataset of unseen ants, the model performed with a true positive percentage of 80%, a true negative percentage of 93%, and an accuracy of 86%.